A ship's coordinates are not measured by looking at the ocean. They are calculated using a physical network of hardware orbiting the Earth. A receiver on the vessel's mast connects to at least 4 of these satellites. By measuring the exact time it takes a signal to travel from space to the ship and multiplying that by the speed of light, the receiver calculates its exact distance from each satellite. The point where those distances intersect forms your raw position fix. That math is inherently unstable. Tiny fluctuations in signal timing and atmospheric interference cause that intersection point to constantly drift. Every second, the system generates a probability circle rather than a pinpoint, resulting in a permanent roaming margin of error of 5 to 10 meters. In the middle of the open ocean, a 10-meter margin of error is irrelevant, but the moment a vessel approaches land, that fluctuating calculation becomes a severe liability. Modern commercial cargo ships are massive physical structures that frequently navigate harbor channels, requiring incredibly tight physical clearance. Imagine piloting a large commercial vessel through a harbor approach that offers a total of only 40 meters of navigable deep water. Map a 10-meter raw GNSS error radius onto that tight geometry, and the mathematical error bleeds over the physical boundaries of the channel banks. The navigation system might show the ship perfectly centered, while the hull is actually scraping the rocks. Relying solely on a raw orbital calculation is statistically unsafe for confined pilotage. Closing that error gap requires a completely separate layer of localized hardware. The solution is differential GPS, or DGPS. This system relies on a physical reference station built at an exact pre-surveyed location on land. This shore station receives the same satellite data as ships. Because its coordinates are locked, it continuously calculates the signal's exact timing error. It then broadcasts a correction wave. The ship applies this, shrinking the error radius from 10 meters down to less than 1. It is the mechanical equivalent of an athlete zeroing a smartwatch against an exactly measured Olympic track right before a race. The base device works, but the localized calibration makes it precise. This sub-meter calibration transforms a rough global estimate into the high-precision tool required to thread a multi-ton hull through a narrow channel. Because this precision GNSS data feeds directly into the electronic chart display and dictates autopilot routing, it is a high-value target for cyber attacks. Many internal maritime networks lack source encryption. A compromised terminal on the bridge can accept forged data as if it were legitimate sensor input. In a network injection attack, malicious software acts as a middleman. It intercepts the legitimate GPS coordinates and alters them before they ever reach the navigation screens. This compromised ECDIS screen capture shows a successful spoofing attack, forcibly offsetting the ship's digital icon. To mask this shift, attackers flooded the system with false data. This dense cluster of overlapping green targets overwhelms the operator, hiding the subtle manipulation of their own coordinates. A navigation screen provides a digital interpretation of reality, not reality itself. If the unencrypted network is compromised, the display can silently convince an officer to steer a perfectly healthy vessel aground. Network injection attacks can also hijack secondary sensors. Here, the raw radar feed overlaid on the ECDS chart is digitally manipulated. The green radar returns are rotated 45 degrees clockwise off their true alignment, projecting coastlines in false locations and destroying the collision avoidance picture. Detecting these manipulations requires watching for strict physical contradictions. A digital position that jumps several miles in 1 second is mathematically impossible. A speed over ground readout of 20 knots when the main engine is barely turning indicates a compromised feed. This vulnerability demands deliberate cross-verification. Every piece of GNSS data must be independently checked against raw radar ranges, visual bearings from the bridge, and analog dead reckoning. The greatest risk on a modern bridge is not a broken instrument. It is an officer trusting a single screen so completely that they stop noticing when an independent system is telling a contradictory story. This principle of questioning your display extends to the radar's tracking modes. If 2 vessels navigating a 3-knot current both register an identical speed of 10 knots on your radar, do they share the same physical collision risk? The answer depends entirely on your reference frame. Sea-stabilized mode tracks movement relative to the water, while ground-stabilized mode tracks the actual path over the seabed. Because tidal currents push vessels sideways, identical speeds through the water result in completely different ground tracks over the seabed. You must verify the stabilization mode to accurately predict where vessels will physically intersect in a heavy current. Safe navigation relies on a strict workflow. Calculate the raw orbital fix, refine it through local DGPS, and cross-verify the data to filter out cyber manipulation. Knowing your exact coordinates on the grid only solves half the equation. You also need to know exactly which way the ship is pointing. For centuries, mariners relied on the magnetic compass, but on a modern cargo vessel, thousands of tons of steel hull and massive electromagnetic fields from the engines severely distort the Earth's magnetic lines of force. The solution is the gyrocompass. It utilizes a rapidly spinning rotor that aligns itself with the true geographic axis of the Earth through pure rotational physics, remaining entirely immune to magnetic interference. A secure navigation setup requires both an incorruptible position fix and a physics-based heading reference. How that gyroscope mechanically seeks true north is the subject of the next module.